Hi, in this video we're going to explain and code the scale.product attention. This comes from this paper called Attention is All You Need from 2017, which represents the very foundation of the transformers architecture. So the way that scale.product attention works is very simple. It takes three input feature vectors, namely the queries, the keys, and the value feature vectors. Then it computes a dot product between the queries and the keys. It scales them, it applies mask. This is optional and it depends if it is the encoder or the decoder block of the transformers architecture. Then it applies softmax, and at the very end it computes the dot product between the vector that we got up to this point and the value input feature vector. And that's it. So now let's start coding. Here I already prepared some code for you to better understand the concept. So let's imagine that we have an input feature vector called x with shape BTC, where B is the batch dimension, which in this case is 2, T is the sequence length, which is 3, and C is the hidden dimensionality or embedding dimension, which in this case I set it to 2. Now, what scale.product attention does is to project this input feature vector into three new vectors, which are our queries, keys, and value vectors. To do so, it uses just a linear layer with its input C number of nodes, and this is important because this must match the hidden dimensionality of our input feature vector x, and as output it has C times 3 number of nodes, and we're doing so for computational efficiency because at the end we can just split the stack tensor and get our 3 new vectors. So after we just call our linear layer and pass x as input, we get our stacked feature vector, and then here we just split this stacked tensor into 3 chunks across the last dimension, which is the 3 times C dimension. Now I can run this cell and we can check the output. So here we are printing the shape of our input feature vector x, which has shape 2, 3, 2. So this is no surprise, we define that right here. Then our QKV stacked vector, which is what we get as output from our linear layer, has shape 2, 3, 6. And this is because here we are multiplying the last dimension by 3. And at the very end, our QKV vectors will have shape 2, 3, 2, because here we are splitting this stacked tensor into 3 chunks. Now, an important concept I want to stress is that no matter how many dimensions are between the batch dimension and the sequence length t, this will just work fine. So let me give you an example. I've added just 4 random dimensions, and now if I run this cell again, this will work again. And as you see, the input feature vector shape has the same shape as before, but between the batch dimension and the sequence length, there are these random dimension that I set right here, and all of the rest will work just fine. And this is a concept that will come in handy later, both inside the scale.product attention and in the multi-head attention block that we will see in the future video. Great, so now we can start coding our scale.product attention. So let me define a function called scaled.product. And this function will take as input 3 vectors, q, k, and v, and mask, which is optional. And just bear with me, I will explain what mask is in a second. Now, based on the paper, what we have to do first is to compute the dot product between q and k. But first, let me do one thing that I always like to do, and I encourage you to do also, is to keep track of the shape of any tensors that you're dealing with. So here we are saying that these q, k, and v vectors have shape b, t, c, and we saw previously that actually there can be even other dimension between b and t. We don't care, this will just work. So I'm gonna define it here with 3 dots. Now we can proceed with computing our attention logits. So we can say attention logits are equal to torch.matmul to compute the dot product between q and k, though we'll have to transpose k and we have to transpose the last 2 dimensions. And let me just explain it right here, what we are doing. So we have q, which has this shape that we define right here. And we are computing the dot product with k, which has the same shape. So to make this work, the last 2 dimensions will be basically the opposite. So we have to invert these 2 dimensions, and what we will get here as output is something of shape BTT. Then what we have to do is to scale these attention logits. And based on the paper, to scale it, we have to divide it by the square root of the hidden dimensionality of one of these input feature vector. So the paper called this dk, and we can get this dimension just by doing q size and selecting the last dimension. And now we can have our attention logits, which will be the attention logits divided by the square root of dk. And now we have to apply mask if it's needed. As said before, this depends if this is a scale.product attention inside an encoder or a decoder block. So this is why it's optional. So for now, just bear with me. I'm gonna say if mask is not none, because by default we set this to none. Our attention logits will be equal to the attention logits, and we can use mask fields where the inputs mask is equal to 0, and we are going to set this to a very low number, which can be something like this. And now we have to apply softmax to our attention logits to get the attention, and we can do this doing f.softmax of attention logits across the last dimension. And what we are missing is just computing the dot product between the attention and our v input feature vector right here. And what we will get is something of shape. So we have attention with shape BTT, right? We got this from here, and we are multiplying this with something of this shape. So V has this shape BTC. So what we will get is something of shape BTC. And now we have to return values and attention. So let's go here to this cell where I call the scale.product function that we just defined, and we pass as input our q, k, and v vectors that we got from projecting our x input feature vector right here. And these 3 vectors, q, k, and v, have this shape 232, which is the same shape of our input feature vector x. So everything is okay up to this point. Now we want to see what we get as output with values and attention. So if we think about what we're expecting right here is that values will have to be of shape BTC, which is basically the same shape of our Q, K, and V vectors. So we want values to have shape 232, and attention will have to be of shape, which is right here, BTT, right? Because this comes from this point. So where we computed the attention logits, then we got the attention out of the softmax of attention logits. So this does not affect the shape at all. So this remains a tensor of shape BTT. So let's see, here values should have shape 232 and attention should have shape 233. Let's run this cell. And yes, we got what we wanted. Now, before wrapping up, let me stress two last concepts. So the first one is the one that I already mentioned at the beginning, and I would just want to test it out again. Here, if I start adding random dimensions between the batch and the sequence length dimension, and we run this cell, so this as before works, and actually should also the scale.product work. And let's see, it works. And let me explain you why. It works because here where we computed the dot product at the beginning between Q and K, we use transpose and we transpose the last two dimensions. So this is why this, let's say, condition is true no matter how many dimensions are between our batch and T dimension. This will just work. So this is the first thing. So let me run this again. Now the second concept is masking. So masking, as I said, it depends if we are inside a decoder or an encoder block. And the way that it works is that, let's say that we define here a mask, which is a triangular matrix of shape. So let me define a tensor, random. Okay, this will have to be of shape TT. And in our case, will have to be BTT. So if we run this, we get something like this, right? And this will be, maybe I can just get the first one so you can see it better. This is just a triangular matrix, right? Where like the diagonal will divide it like the values between all the zeros, basically. So this is just a simple triangular matrix. And this is passed in the decoder block where we don't want the attention to see like the words that comes after the words at certain point. So if I'm a word or a token at position T, I don't want this token to see all the tokens at position T plus 1, T plus 2, and T plus n. And if we pass this mask to our scale.product attention function, actually this will not affect at all the shape, and we can run it, right? This works just fine. What will affect is the attention. So we can see that if we print the attention, you see right here that this is, let's say, a weighted average, but we are leveraging the triangular matrix. So token at position T will not allow to see all the tokens at position T plus 1, T plus 2, or T plus n. This depends on the sequence length of our input feature vector. So maybe I can even run this without passing a mask. and print the attention right here, and you will see that this changes, right? So this will be just a weighted average across all the sequence length. Instead, here we are using the triangular matrix. So in the decoder block, especially for language translation, we want to use a mask. Instead, if we are inside an encoder block for other tasks, like for example, sentiment analysis or classification, we don't want to use masks. So we want all the tokens to communicate to all the other tokens, no matter the position of these tokens. Great, so hope this helped you understanding the scale.product attention. And in the next video, we are going to see the multi-head attention block. So stay tuned, subscribe to this channel, and see you in the next one. Cheers!